Hello everyone, my name is Ke. I'm a third-year PhD student in information science at Cornell University. Today, I'm presenting our work, EyeEcho, on continuous and low-power facial expression tracking on glasses. This work is accomplished in collaboration with Ruidong, Siyuan, Boao, Mose, Francois, and Chen. With the rapid development of wearable devices, especially VR/AR headsets, continuous and high-quality facial expression tracking is made possible for video calls in the virtual environment. Commercial products such as Apple Vision Pro is impressive at providing users with the ability to understand their facial expressions. However, it also has its own drawbacks in terms of the cost and power consumption. Instead, we would like to propose a continuous facial expression tracking technology on glasses which many people wear every day. To enable it, the presented technology should be small in size, cheap, and low power so that it can be deployed on lightweight glasses which most people can afford and can be used all day long without being charged. Our solution to this problem is to place acoustic sensors on a pair of commodity glasses to reconstruct users' facial expressions continuously. It adopts the acoustic sensing technique, so it is low power and can last as long as 14 hours with the battery of Google Glass. The system was evaluated in different real-world scenarios, including different noisy environments and a semi-in-the-wild study. Lastly, the entire hardware system costs as low as $50. So, why do we need a pair of smart glasses to reconstruct users' facial expressions continuously? As we all know, facial movements is one of the most critical human behaviors that people use to interact with the physical world. Understanding people's facial movements is the basis to understand many human activities, such as the emotions people express, the physical activities people conduct, and the health conditions of people. The most traditional way of providing continuous facial expression tracking is based on frontal cameras, such as the True Depth camera on iPhone. These frontal camera-based methods are excellent in performance because usually they don't need new users to provide training data. However, they don't work well when the users are in motion and have some occlusions in front of them. Therefore, some researchers attempt to solve the problem on wearables. Commercial products such as Apple Vision Pro and Meta Quest Pro place multiple cameras on headsets dedicated to reconstruct users' facial expressions. They achieve promising performance, but cameras are known to be power-hungry, so it is not very practical to be deployed on smart glasses, which usually have batteries of limited capacity. Acoustic sensors, on the other hand, are relatively low power compared to cameras. One of the prior work from our lab utilizes speakers and microphones on a pair of earphones to track facial expressions. It maintains low power consumption while achieving impressive performance. However, not many people are used to wear earphones all day long, while lots of people do wear glasses throughout the day. It is unclear whether the technique can be applied to glasses directly because the acoustic sensors mainly travel behind users' ears in this system, which are quite different from the case when the sensors are placed on glasses. Researchers explore the possibility of deploying acoustic sensors on glasses and are able to distinguish 6 discrete upper facial expressions. Yet, to the best of our knowledge, there's no prior work that is capable of tracking 4 facial expressions continuously on glasses. As a result, we would like to design and implement the first smart glasses that can track facial expressions continuously while being low power and minimally obtrusive. The technique behind EyeEcho is called active acoustic sensing. We use speakers on the glasses to emit encoded acoustic signals towards the face and use microphones at the same position to capture the reflected signals. By analyzing and learning the unique patterns, we are able to provide high-quality facial expression reconstruction continuously. So, what's the principle of operation for EyeEcho in details? First, we need to understand what active acoustic sensing is. To apply active acoustic sensing, first we emit encoded signals towards user's face. For EyeEcho, we chose FMCW signal which is frequency modulated continuous wave, because it has been applied in various applications to track human activities and achieve satisfactory performance. After the emitted signal is reflected by the user's face and captured, we apply a bandpass filter on the received signal to only retain the signal in the frequency range of our interest, and then perform the calculation of cross-correlation continuously between the reflected signals and the transmitted signals to obtain the unique acoustic patterns associated with the facial movements, which we call echo profiles. The differential echo profiles reflect the change of the objects in the environment, including the movements of the user's face. We visualize the change of the differential echo profiles in this video together with the facial expressions performed. As we can see, when people perform different facial expressions, the corresponding differential echo profiles will change accordingly. It also captures small facial movements as subtle as blinking. To track facial expressions continuously, we apply a sliding window on the differential echo profile and feed these features into a customized deep learning model based on ResNet. After properly training the model, it gives us 52 blend shape parameters representing a facial expression, corresponding to the input acoustic patterns. After discussing our principle of operation, then I want to talk about the detailed implementation of our EyeEcho system. We use a Bluetooth low-energy module to control the signal transmission and reception, and it is also responsible for transmitting received data to a local server via Bluetooth. To emit and receive acoustic signals, we picked miniature speakers and microphones which can be properly placed on wearables. PCBs are customized for all these components. We explored 3 sensor positions on the glasses and compared the system performance through a pilot study. Considering the performance and the obtrusiveness of the system, we decided to put the acoustic sensors at position 1. We believe that with our EyeEcho system instrumented, the prototype looks similar to a pair of normal looking glasses. Users are able to wear our smart glasses as they usually wear eyeglasses. We validated the performance of our system in 3 user studies. In all user studies, we used a frontal true depth camera on iPhone as a ground truth. It gives us 52 blend shape parameters representing the status of different parts of the face. We used MAE, which is short for mean absolute error, between the prediction of our system and the ground truth as a main evaluation metric. The maximum value of MAE is 1000 theoretically, as determined by the ground truth parameters. To help people understand how similar the prediction looks to the ground truth visually when different values of MAE are reached, we plotted the predicted facial expressions on the different MAE. As displayed in the figures, the smaller the MAE is, the more similar the prediction is to the ground truth. For the facial expression open mouth, when the MAE is around 40, the prediction is visually highly similar to the ground truth. Then let's take a look at another facial expression open eyes. It is also true that when the MAE between the prediction and the ground truth reaches 40, they are visually similar to each other. For subtle facial movements like blinking, the value is about 20. With the evaluation metric determined, the system was first evaluated in a controlled in-lab study in which the participants were instructed to perform a predefined set of facial expressions while sitting and walking around. In total, 12 participants were involved in this study, and the device was remounted between every 2 sessions. The study results demonstrate that only 4 minutes of training data collected from new users lead to an MAE of 25.7 for the sitting scenario and 30.5 for the walking scenario. We visualized several randomly selected samples from the study results to showcase the system performance. When the MAE is around 15, 30, and 35, the prediction is visually similar to the ground truth. When the MAE reaches 50, one starts to notice the difference between the prediction and the ground truth, but the error is still within the acceptable range. This validates that if the system maintains a tracking error at around 40 MAE, it reaches a promising tracking performance. Following our in-lab study, we further experimented the system performance under real-world noisy environments. We recruited 10 participants and asked them to test the system under 3 noisy environments, which are meeting room with loud noise played, cafe with people talking, and street with vehicles and pedestrians passing by. The noise level in these environments was measured to be between 55 and 70 dB. By plotting the received signal and the noises in the frequency domain, we can see that the noises in the environments are mainly in the audible frequency range, while the encoded signal in our system operates from 20 to 24 kHz. This means that most of the noises should be filtered out by the bandpass filter and have little impact on the system performance. This assumption is proved valid for the experiments conducted in the meeting room and the cafe. However, the performance decreased when the participants moved to the street. To explore the rationale behind this phenomenon, we conducted another experiment by putting the hardware outside on street without anyone wearing it. It turned out that the shape of the received signal changed quickly after the system was brought outside. Given that this study was conducted in winter at Cornell, Ithaca campus, where half of an year is freezing with snow, we believe that the difference in the environmental temperatures changed the characteristics of the speakers and the microphones, which further affected the system performance on tracking facial expressions. Lastly, a semi-interval study was conducted to evaluate the system in a less controlled study setting. 10 participants were invited to a one-bedroom apartment to participate in the study. Different from previous studies, they were allowed to perform whatever facial expressions they want while finishing different activities such as watching videos, reading, talking, walking, making bed, washing dishes, and using the microwave oven. The study was completed in 3 different rooms, including living room, bedroom, and kitchen, on 2 different days, while the training data was only collected in the living room on the first day. The tracking performance of our EyeEcho system is comparable across 2 days on 44.4 MAE for day 1 and 45.5 MAE for day 2. The figure demonstrates that the system performance varies across different rooms because the training data was only collected in the living room, but overall remains satisfactory in all scenarios. We also visualized some randomly selected samples from this study. These visualized results display the promising tracking performance of our system in more real-life and less constrained experiment settings. EyeEcho can potentially be used for multiple downstream applications. First, it can be a vital feature added to commodity VR headsets and smart glasses. Facial expressions tracked on these devices can be used as interactive tools and to display more realistic avatars for users. Moreover, as discussed at the beginning of the presentation, facial expression tracking can be adopted to understand users' physical activities, such as documenting their eating and drinking behaviors throughout the day. Besides, facial expressions are closely related to users' health conditions, especially for patients with neurodegenerative diseases, such as Parkinson's disease and Alzheimer's disease. Facial expressivity is an effective indicator of the progression of their diseases. Furthermore, the technology embedded on smart glasses can be used as an easy way to send emojis to your friends hands-free when your hands are occupied with other tasks. That's all I would like to share about this paper today. I'm open to any questions. Thanks for listening.